This video is part 2 of the chain rule lesson, section 3.6 in the calculus text. If you haven't watched part 1 of the chain rule video, please go back and watch part 1 before watching this video. Applying the similar concepts to what we did with the chain rule in the first video, we'll see that we can find the derivative or the slope of a parametrically defined curve. Recall that with parametric equations, we get equations x and y defined independently in terms of a third variable t. In order to find the slope of a parametric curve, we can calculate the derivative dy dx by taking the derivative of y with respect to t and putting that over the derivative of x with respect to t. As we saw with the chain rule, if we cancel common factors, we get the derivative we want, which is dy over dx. Before taking the derivative with example 4, let's first have a quick review of what parametric equations are. In parametric equations, x and y are defined independently in terms of a third variable t. And so if we are plotting points, we have t and x and y. So let's start with 0. If we plug 0 in for t in the x equation, 5 times cosine of 0 is 5. 5 times sine of 0 is 0, because sine of 0 is 0. So that corresponds to the point with the coordinates 5, 0. Plugging in another easy coordinate to plug in, when t is pi over 6, we can take the cosine of pi over 6, which is root 3 over 2. That gives us an x-coordinate of 5 root 3 over 2. The sine of pi over 6 is 1/2, so we get 5 times 1/2, or 5 halves. Converting that into coordinates, we get 5 root 3 over 2, 5 halves. With decimal coordinates, this would be approximately 4.33, 2.5. Let's try a third point. At pi over 4, cosine of pi over 4 is root 2 over 2, so we get 5 root 2 over 2, and also for the y-coordinate, 5 root 2 over 2. So our point is 5 root 2 over 2, 5 root 2 over 2. In decimals, that's approximately 3.54, 3.54. At pi over 3, sine or cosine of pi over 3 is 1/2, so we get 5 halves, and sine of pi over 3 is root 3 over 2, so we get 5 root 3 over 2. Coordinates of our next point are 5 halves, 5 root 3 over 2, which puts us at approximately 2.5, 4.33. And let's try one more point. At pi over 2, cosine of pi over 2 is 0, sine of pi over 2 is 1, so we get 5 times 1, which is 5. Coordinates of that point are 0, 5. And now we can go ahead and plot those points. On a grid. So 0, 5 would be here. 4.33, 2.5 be about there. 3.54, 3.54 be about there. 2.5, 4.33 is about there, and 0.5 would be there. So we see that these are actually the coordinates of points on a circle. And so what we're looking for is the equation of the tangent line that we get when t is equal to pi over 3. So that corresponds to this point, 2.5, 4.33. So we're looking for the equation of a tangent line at that point. So we need the slope of the curve. Since we have x written as a function of t, we can calculate the derivative dx dt. That would be negative 5 sine t. Similarly, since we have y written as a function of t, we can calculate the derivative dy dt, which is 5 cosine t. Now dy dx is equal to dy dt over dx dt. Remember, if we cancel the dt's, we have dy over dx, which gives us rise over run for our tangent line. So in this problem we have dy dt is 5 cosine t, and dx dt is negative 5 sine t, which gives us negative cosine t over sine t. Now plugging in our t value, pi over 3, we get the slope at t equals pi over 3 is negative cosine of pi over 3 sine of pi over 3. Evaluating this expression, we get negative 1/2 over root 3 over 2, which simplifies to negative 1 over root 3. Now we have the point from up above, and we have a slope, negative 1 over root 3, so we can write the equation of the tangent line, y minus 5 root 3 over 2 equals our slope times x minus the x value 5/2. Now we have the equation of the tangent line. And that completes the lesson on chain rule and derivatives of parametric equations.